I want to find a Taylor series for natural log of x, and I really like this example for a couple of reasons. It's a little bit of a complicated function, but it ties to some very simple things as well. So to do this, I'm going to use the definition of Taylor series. I'm going to need to pick a value of a to center my Taylor series. And my first step is to start taking derivatives of this thing, see if I can find a pattern, and then I'll see if I can find a convenient value of a to center my series at. I'll think about the graph of natural log of x as well, just to refresh my memory on some important properties of that function. All right, so f is natural log of x, that's f0 here. If I evaluate that at, well, I don't want to evaluate that at any specific numbers yet. We'll talk about that in a minute. Let's try to find a pattern for derivatives. So first derivative is 1 over x, or if we're taking more derivatives, I want to think of this as x to the negative 1. Second derivative, I apply the power rule, I get negative x to the negative 2, which is negative 1 over x squared. Now third derivative, I get negative times negative 2, so positive 2x to the negative 3. And I'm wanting to find a pattern here. I see a couple of things happening. I'm seeing a plus minus plus minus. I'm seeing the power of x grow by 1. But then I'm kind of curious, I had a 1, and a 2. I don't know what the numerator is going to be next. I'm curious about that. So fourth derivative, using the power rule, I get negative 6x to the negative 4. And I'm noticing for this pattern, this 6 came from multiplying 2 by 3. So I'm going to think of this as 3 times 2 for the purposes of finding that pattern. And then I know this is also negative 6x to the negative 4. So fifth derivative, 24x to the negative 5. That 24 is coming from 4 times 3 times 2, so I'm recognizing that as 4 factorial now. And it's positive, so 4 factorial over x to the 5th, or 4 factorial x to the negative 5. And now I think I've got the pattern. So I think f to the 6th, the 6th derivative, will be 5 factorial over x to the 6th, and I think it would be negative. So now let's check that. If I take the derivative, I get negative 5 times 4 factorial. That's negative 5 factorial. I get x to the negative 6. So this is working. Now, I want to get the nth derivative. So I think the numerator and the denominator aren't that hard to see. The denominator should be just x to the n. The numerator looks like it should be n minus 1 factorial. And then to pick up this alternating negative and positive, I'm going to do negative 1 raised to a power. And when I raise it to a power, I'm just going to raise it to either n or n plus 1. So if I raise it to the nth power, then when n is even, I will have negative 1 to an even power. That would give me a positive, but I want a negative. So I'm going to try n plus 1. Now what that's going to do is every time I get an even number as my n, I'll have -1 raised to an odd number, which will give me a negative. That's what I have here. That's what I have here and here. So I've got the pattern. Now that I have the pattern for that derivative, I want to think about what value of a convenient value of a that I can center this at. Now, I know I'm not going to center this at x equals 0 because my function's not even defined there. I'm not going to use any negative numbers. So I'm just thinking of positive numbers to plug in for a. And what this a is going to do is I'm going to feed it into these derivatives, and then I want something simple to come out. So when I feed x equals a into these derivatives, if I want something simple to come out, then a really nice choice for this is x equals 1. If I plug in x equals 1, then all the denominators just go away. So I'm going to write that up here. I'll write it in a different color. If I take the nth derivative and evaluate it at x equals 1 for natural log of x, then I just get -1 to the n plus 1 times n minus 1 factorial. And I get over 1 to the n, which is 1. Also, the original function was natural log. Natural log of 1 is 0. Because the definition of natural log of x is what power do I raise this hidden base by, the hidden base of e? What power do I raise e by to get x? So the power that I raise e by to get 1 is 0. So that y value is 0. So this works for all n greater than 0, and then for the original function, natural log of 1 is 0. So that constant term goes away. That means I'll be starting at n equals 1 in my natural way to write this series. Now let's think about what that looks like. I'm going to first write this general series for it, and then I'll write it term by term. So again, n equals 0 will go away, so I'll start at n equals 1. And then my nth derivative evaluated at a is this thing. But notice, when I divide that by n factorial, so I take this and I divide by n factorial like I'm supposed to for this coefficient, then this n minus 1 factorial, if n is 5, for example, that's 4 factorial, that's 4 times 3 times 2 times 1. 5 factorial, 5 times 4 times 3 times 2 times 1. So in the numerator I have something like this, and in the denominator I have this. So you can see everything is going to cancel out except for the largest power on bottom, the n. So when I simplify this coefficient, I'm just going to get -1 to the n plus 1 over n. And then I'm going to erase this now to give a little space here. A was 1, so this is x minus 1 to the n. Alright, so that's my series. I said I was going to write it out term by term, but before I do that, I actually don't want to write it out term by term for this general function, because what I have in mind is to do this for x equals 2. There's a couple reasons for that. The main reason is that if I approximate this number natural log of 2 using this series, then a really nice example of a series comes out that I want to think about. So I plug in x equals 2 into this. It gives me a series for natural log of 2. You probably don't have a good value in your head for what natural log of 2 is, but you do know that natural log of 1 is 0 and natural log of e is 1. So this should be between 0 and 1, closer to 1 than 0. When I plug in x equals 2, I get 1 to the n, and that's just 1. So this series looks really nice and simple. I'm going to write it like this. I'm going to pull this minus 1 to the n plus 1 out in front, and then just write it as 1 over n. So natural log of 2, if I plug in n equals 1, I get negative 1 squared is positive 1 times 1. So for my approximation of natural log of 2, I'm starting out at 1. And now, part of my purpose for picking this is to think about this geometrically. Alright, so I'm going to draw this function natural log of x again. It looks something like this. This is x equals 1. If I go out to 2 and then 3, I know that e is around 2.7, so maybe around here. And when I take natural log of e, I know that's equal to 1. So now, when I look at natural log of 2, that means I'm here on the graph. It should be this value. And notice, when I'm approximating this, I'm starting at 1. So, if I look at my first term, so I'm going to lay on top of this another graph where I'm graphing a sequence of approximations. My first approximation is 1. So I'll plot that here. This is a graph on top of the already existing graph. That's my first approximation. Now for my second approximation, I plug in n equals 2 and add something to 1. So when I plug in n equals 2, I get negative 1 to the third times 1/2, so minus 1/2. So my second approximation is 1 minus 1/2, which is equal to 1/2. So maybe that's around here. 1/2 maybe is around there. So notice what's happening. This green value is what I'm trying to actually approximate. I started out with 1, and then I subtracted something from it. On my next one, I'm going to add something to that, and then I'm going to subtract and add and subtract and add. Each time I add or subtract, the number that I'm adding or subtracting is smaller in absolute value than the one before it. So as I jump down and then up and down and up, I'm jumping smaller and smaller distances as I move out and get better approximations. Plug in n equals 3, I get a plus 1 over 3. Now it's a little harder for me to do in my head, but I've got 0.5 plus 0.333, so that's like 0.83. 0.83 might be around here, something like that. So notice, when I made my first approximation, the error between my approximation and the actual value was that distance. And then I jumped a distance equal to this purple line to get to my next approximation. All right? Now, from there, for my second approximation, the error is this distance. And from there, I jumped this purple distance to get to my next approximation, which was here. So what happens as I subtract and add and subtract and add? I'm getting closer and closer to the actual value. But also, each time I make a jump, that jump is larger in absolute value than the error of my approximation before I made that jump. So I know what this pattern looks like. It would be minus 1/4 plus 1/5 and so on. And what I know about the approximations that I'm getting from this, if I cut this thing off, for example, here, and just add these terms together, then what I know is that whatever decimal approximation I get from that, the error of that approximation it has to be smaller than this 1/7, because the error is like this red distance, and then the next value is my purple jump. So if I have an alternating series, it's really easy for me to get an upper bound on the error. This particular series happens to be converging pretty slowly. So to get good approximations, I would have to go out far. But you'll deal with other ones, especially with sine and cosine, where it converges a lot faster, and so you can get to a much smaller error more quickly. One last thing I wanted to point out about this particular example is that this is almost exactly the harmonic series where you do the sum of just 1/n. That sum of just 1/n diverges. It gives you something infinite. So this is a strange case where if you take all of these terms and you make them all positive, then you get something infinite. But if you alternate terms between positive and negative, you get something finite. It's good to have this example sort of in your repertoire, in your belt. You want to have some very basic examples that you've worked through multiple times that you can use for building up intuition about more complicated functions and more complicated actions that you take with those functions.